Second question here in this third chapter. So this is about how, let's see, for pumping a balloon, both the volume and the radius of the balloon are increasing. So you're pumping up the balloon, the volume is increasing as you put air into it, and also the radius is changing. And what's the relationship between them? Okay, in a related rates problem, the idea is to compute the rates of change of one quantity in terms of the rates of change of another, and hopefully the other one is more easy to measure. So for example, with a balloon, you can kind of measure the volume by the amount of air that's in it, more or less, up to problems with pressure. The idea is to find equations relating to two quantities and then use the chain rule to differentiate both sides with respect to time. So let's see how this might work. So I'm not really 100% sure what I want to put in here. So you have a balloon. Well, imagine it's a sphere. And you got the radius and the amount of stuff. And imagine that they're changing in time. So you can say that V, the volume, is a function of radius. But if there's a change in time, you have the volume as a function of radius, but the radius is a function of time. And so what we're going to do, I think, is differentiate the volume V of RT with respect to time and see what we end up with. So what we're going to say is the derivative of volume with respect to time. So we'd have to differentiate this thing. Now there's an outside and an inside, so that means you need to use the chain rule. So the chain rule says differentiate the outside. So the outside is V, you get V dashed. Evaluate at the inside, which is just R. And then the chain rule says you must multiply by the derivative of what's inside, which would be R dashed of T. Now another way of writing V dashed of R, that's the derivative of V respect to R, and R dashed of T is the derivative of R respect to T, is that dV dt is equal to dV dr times dr dt. Now what you have to be on top of here is that derivatives are rates of change. So the object on the left is the rate of change of volume with respect to time, which we just call the rate of change of volume. The second quantity is the rate of change of volume with respect to radius, and the third quantity is the rate of change of radius with respect to time. It's reasonably easy to come up with this formula. Now what I'm going to do works. It doesn't really make sense, but it gives you the right formula. So you work like this. So you say dV dt equals. So what you do is you spread out the dV and the dt, and then you can put in any other variable that you want. You could put in area, for example, but we'll usually be interested in something else, like, for example, here, radius. So that highlighted formula, this is how you would form it. Okay, and we'll see it work in examples. So it's a relationship between rates of change of volume with respect to time and radius and the rate of change of radius. Okay, now this is also the way we derive the formula for parametric differentiation, because you could do this kind of another way around. You could say that R is a function of T, V is a function of T. So all I'm saying there is that the radius is changing with time, the volume is changing with time. And then, so what we did above is very similar to something where we would have said y was a function of x, which is a function of t, and we would have differentiated y with respect to t and used the chain rule and got something that was useful. But say, let's go back in terms of the previous chapter. You can write dV dr equal to, that should be a bigger V maybe, dV dt divided by dx dt, and not dx dt, dr dt. And then if you want, you can get the formula above by multiplying both sides by dr dt. So you get dV dt is equal to dV dr times dr dt. which is the same formula as the highlighted one. Now, essentially, it's saying that when you've got any function y of t, you can just write out basically what I did just above. You can just spread out the dy and the dt and then just throw in another variable, a suitable variable. Now, one thing we should talk about is the units of dy dx, because we're engineers, or you're engineers. So what about the units of dy dx? Now, dy dx is a rate of change of y with respect to x. So it has the same units as a change in y over a change in x. And the units of a change in y are the same as the units of y divided by the units of x. And then the next bit, you're just going to have to take my word for it, is the units of y divided by the units of x. So this square brackets means units of, which is the same thing as the units of y. So you could write per units of x, or you could write units of y per units of x, like that. They're the same thing. It's probably worth doing an example. An example of this. So velocity is rate of change of distance with respect to time, and the units of ds dt are the units of s divided by the units of t, and the units of s distance are meters, and the units of time are seconds. So you get that the units of velocity is the units of ds dt, which is meters per second. Now we kind of just on this line we've gone from kind of parametric to related rates. You can also go from related rates, I think, to parametric. So you could do what am I trying to say here? So you can write dy dt is equal to dy dt, spread it out, and put in the other variable that's somehow related, which would be dx. And then you can solve this for dy dx by dividing both sides by dx dt. So that's an alternative way to derive, well, it's not really, it's just another way of writing it, but I'm just saying that this is linked. Now, one thing you might have to use is this dv over du is 1 over du dv. Now, why that's true is a little bit messy. You're just going to have to take my word for it. I'll show you where it might come up. So say, for example, you're talking about dr dt, and you say, okay, dr dt, that's good, and you put in, say, the volume. Now, dr dt makes perfect sense. It's the rate of change of radius with respect to time. dv dt makes perfect sense. It's the rate of change of volume with respect to time, but dr dv is a little bit messy for us. So what you would do instead is you would write dr dt as 1 over dv dr, and that makes more sense, the rate of change of volume with respect to radius. So sometimes if you're stuck, you might have to do this. Okay, we may or may not see an example of this. Right, so let's do some examples and see how this goes. So first example, consider water flowing into a large upturned cone. So we've got water flowing into this kind of a yoke, such that the ratio of radius to height is 1 to 2. Now, you can be getting a bit bothered here, but the formula is given down there, so it's okay. Then, if the height of liquid in the cone is h, it can be shown that the volume of liquid is 1/12 pi h cubed. Okay. Suppose the water is flowing into the cone at a rate of this. Find how... Okay, so this is all a bit confusing. You need to slow down anyway, first of all, and identify some things that we know. Okay. So if the water is flowing into the cone, that's a change in volume, and if it's given at this rate, this is the rate of change of volume. So this number here, 100%, is dv dt. So water flowing in is a change in volume, and if you have the rate of change of how, if you see the rate at which the water is coming in, you know how much the volume is changing. It's 0.05 meter cubed per second. So that's the first thing. The second thing is that what are the two variables that we're interested in that are related here? The related variables are the volume and the height. Okay, now what you want to do is to so we spoke about the thing on the previous page about it. If you're stuck, you might have to do this. Now, the way to avoid having to do that is to kind of see which of these two things is more complicated. And what I mean by that is, like, what depends on what. Now, strictly speaking, when you know the volume, you can calculate the height, but really it's a lot easier if you know the height, you know the volume. So I'm saying that volume is more complicated because it's easier to see that the volume depends on height. So we're just saying volume is a more complicated object than height. And when you're forming your chain rule, this thing here in the middle, you differentiate the most complicated thing. So if we look at the thing where we got stuck down the bottom, we had volume and radius, and rather than the complicated thing volume, we differentiated the easy thing radius, and that's when we ended up with problems. You need to differentiate the complicated thing. So the complicated thing is dv dt. So now we spread this out, and now we put in the less complicated thing, which is height. Okay, now one thing is worth pointing out, very important, what are we actually looking for here? Find how fast the height is changing. So this is actually what we're looking for. Okay, so the thing is, we know dv dt because it's given in the question, and we can calculate dv dh. That's the derivative of volume with respect to h, but we can do that because we know the relationship between volume and height. So we'll do that now. So let's differentiate volume with respect to height. So I've got 1/12 pi h cubed. Now what I recommend is we'll fix the constant 1/12 pi, and then the derivative of h cubed is 3h squared. Now you can simplify that a little if you want, but we don't really need to. So we know dv dt, we know dv dh, and what's actually interesting is we're interested in the point where h is equal to 1. So we should substitute h equal to 1 into this to find dv dh at the point we're interested in. So this would be 1/12 pi by 3 by 1 squared. Now you're an engineer, you want to do decimal approximations, and that's fine. Maybe use 4 significant figures. So no, I normally prefer keeping it my own way, but we'll go along what you would like. So 4 significant figures. Now I don't want to write equals because it's not equal. It's approximately equal to 0.785. Now it's 39, so that should round that to 4. Okay. So putting everything together, we have dv dt. Now, what does it mean putting it together? I mean this yoke. So dv dt is 0.05 is equal to dv dh, which I just calculated to be 0.7854 times dh dt, which is what I'm looking for. And therefore, to find dh dt, which is how fast the height of liquid is changing, I just divide both sides by the 0.7854. So you have 0.05 divided by, now one of the things that would be good is if I kept the pi a bit longer and round at the end, but look, it's not a massive deal. 0.7854. So I'm dividing both sides and I get 0.0 to 4 significant figures, 636. Now it's 86, so that rounds to 9. And now what about the units? So the units of dh dt is the units of h divided by the units of t. The h, as we can see, is in meters, and the time, as we can see, is in seconds. So about every second, it's going up about 6 centimeters at that point. Now, actually, so a bit later on, of course, like because it's an upturned cone, the radius is going to grow slower. So this is like when you're blowing air into a balloon at the start, the radius changes quite quickly, but then it slows down. Okay, which we're going to learn about here. So another example. Air is being pumped into a spherical balloon so that its volume is increasing at that rate. So, okay, so in terms of the variables, we're looking at, how did we do this? use purple. Well, what do we see in the question? We see volume, we see radius. These are the things that we're interested in. And it says that the volume is increasing at a rate of 100 centimeters cubed per second. So this is the rate of change of volume. Okay, so we know dV/dt is 100 and we want to find dr/dt. So what we're going to do is write down this thing with volume and radius, and which one is more complicated? Volume. So do dV dr is, sorry, not dV dr, dV dt is dV. So spread this out and then bring in the other variable, which in this case is dr. Okay, I'm just looking at the next bit. There seems to be loads of space here on this question, and I'm not sure why. Let's just drive on here. I think just we can just ignore these bits, because it's just saying that there's a relationship between volume and radius. We know that the volume of a sphere, and this would be in the tables, 4/3 pi r cubed. Okay, so what are we looking for here? We're looking for how fast is the radius of the balloon increasing. So we're looking for the rate of change of radius. That's what we're looking for. So hopefully we know everything else. So what have we got? dV/dt we know. Now let's just calculate dV dr, and then we can put in the r, the value of r a little later. So dV/dt is equal to 100. What's dV dr? So we want to differentiate this volume with respect to radius. So we have a constant 4/3 pi. I recommend fixing that. And then differentiate r cubed. The derivative of r cubed with respect to r is 3r squared. We can simplify that if we want to, but we don't really need to. Times dr/dt. Now what we're interested in is when the diameter is 50. Now if the diameter is 50, the radius is half that, it's 25. So what we want to do is we want to evaluate this at r equal to 25. Now we're using all centimeters here, so we'll stick to the centimeters. So if we do that, we get 100 is equal to, so last time we would have calculated the derivative separately and then put it in here. We're kind of putting it all in the middle. So I want to calculate 4/3 times pi times 3 times radius, which is 25 squared. And I get 2,500 pi, and we'll go for the 4 significant figure rounding, which is 7854. Now I prefer what I said first, but look, we'll run with this. And then, so all you have to do here is to divide both sides by 7854. So you have that dr/dt is 100 divided by 7854. 7854. So we get 4 significant figures. This should be an approximate because we're going with the rounding, the decimal rounding, 0.01273. And look at the units. It should be units of radius divided by units of time. The distance here is measured in centimeters and the time is measured in seconds. So that's that question done. And then, well, this is no need for this. Right. So we'll keep going. Another question. Obviously, these need practice. So this one is a bit tough. This one's a bit tougher. Now we're going to look at 2 options, I think. The second option is probably easier, but possibly a bit confusing. So the surface area. So if we talk in terms of variables, area and volume. Okay, now the issue is we haven't got, like, we can't, like, you can formally write, and we'll do it down the bottom. Let's do, so volume is more complicated than area. So you end up writing something like dV dt is equal to dV dt and then put in the other stuff, which is dA. But you're actually stuck here because you don't know how to differentiate volume with respect to area. So what you have to do here is you have to split up dV dA. Now this turns out to be easier in the end, but probably easier to do the longer way. So now put in the other variable that's locking around. Well, that would be the radius. And then what happens? Well, so dV dt is the rate of change of volume with respect to time. That's useful. dV dr we can calculate. dA dt is the rate of change of area with respect to time. The thing in the middle is weird. The derivative of radius with respect to area. We can do the derivative of area with respect to radius. So this is this situation where we're kind of stuck, where you can flip it. So this is equal to dV dt times 1 over dA dr times dr dt. And I think when we actually do the question, you'll see that we want to know dV dt. So this is what we'll be looking for. In terms of dV dt, will have to be in the question. Oh, sorry, I made a donkeys out of that. Sorry, my bad. That should be dr. dr we can calculate. dV dr, excuse me, you just differentiate. dA dr we can calculate, and hopefully dr dt is in the question. Now I'm stuck. No, I'm not stuck. I'm just an idiot. Sorry. This one in the end is dA dt. And that is given in the question. My bad. So although very complicated, and in fairness, what we're going to do is also going to be complicated, that's probably the easiest way of doing it. So the other way would look something like this. So you'd note that there's a relationship between, we've got formulas for the surface area of a sphere and the volume. So we've got that the area of a sphere is 4 pi r squared, and the volume of a sphere is 4/3 pi r cubed. So now it's difficult. So we're thinking, okay, we have this is area and volume, and we say, okay, so what we could do is something like this. We could say, okay, let's differentiate area with respect to time, and we get the area, the time, and we'll put in the other thing we know about, which is radius. And let's do similar for volume. Yeah, as these questions go, this is a hard one. Let's put in the other thing that's knocking around, which is radius. Okay, now let's look maybe at this point, what are we actually looking for? The question is looking for the rate of increase of volume. So this is what we're looking for. Okay, now if we kind of analyze what we know and what we don't know, dV dr, we can differentiate volume with respect to radius and chuck in r equal to 20. This is no problem, but we do not know dr dt. There's nothing telling us what is the rate of change of radius. If we come over onto the left-hand side, dA dr is no problem because we can differentiate area. We don't know dr dt, but so we'll just put that as an unknown. What about dA dt? Well, dA dt is actually in the question because the area is increasing at a constant rate. So that's dA dt. So the area is increasing at that rate. That is the rate of change of area. So we know this. And if we know dA dt and dA dr, then we can find this, and then we can substitute it into that, and then we'll find dV dt. So not particularly easy or anything like that. Okay, so let's do maybe the next line on both of them. So dA dt, as we mentioned, you might have to pause and look back here, it's tough, is 500. dA dr is the derivative of area with respect to radius. So I'm differentiating 4 pi r squared. For me, I fixed the constant 4 pi, and the derivative of r squared is 2r times this dr dt that I don't know about. And over on the left hand side here, I can write dv dt, which is what I'm really looking for, is equal to dv dr. So I need to differentiate volume with respect to radius. So I'm differentiating this 4/3 pi r cubed. I'll fix the constant 4/3 pi, and the derivative of r cubed is 3r squared. Okay, times the r dt that I don't actually know. Now what I'm going to do now is I'm going to evaluate the derivative of area and the derivative of radius, of volume at r equal to 20. So I'm going to substitute r equal to 20 into that and r equal to 20 into this. So I'm going to get 500 is equal to, so that's 4 pi by 2 by 20. And are the units all centimeters? Yeah, so we'll just run with centimeters. So this is 502.7 times dr dt. And then we can find dr dt by dividing both sides by 502.7. So I get 0.9946. And if I want, I can put in the units centimeters per second. So now over here, I get, if I substitute in the r equal to 20, so that's 4/3 times pi times 3 times 20 squared. And I know that dr dt is well, I'll leave that out for a minute. So this is approximately, actually I should be adding a few more approximately's. So this is approximately 5027 times the RDT, which I've just calculated as 0.9946. Multiply those together at 4 significant figures, 5027 by 0.9946. We're talking 4999.8, which is 5,000. And it is, rate of change of volume with respect to time. Units of volume over units of time. Units of volume are centimeters cubed, and time is seconds. Okay, so that's by far the hardest of those.